So hopefully you saw the previous video of this series, as there was a lot of valuable and very intuitive information presented in it. Nevertheless, this video will be a more I'll derive a means of solving an equation of this type, and it'll be more for the hands-on approach, but there's a lot of valuable information in the previous video that even if you might not need it necessarily to be able to solve this kind of equation, it's still useful to have as a baseline. So, as already established in the previous video, an equation of this type really is just partial f with respect to x dx plus partial f with respect to y dy, and it's equal to 0. And for anybody familiar with multivariable calculus, this is a total differential, or for anyone in single variable calculus terms, this would be an implicit derivative. So hopefully we're on the same page right now. Then you have already figured out that the object is to find what function is this the implicit derivative of. So for some unknown function of two variables, let's just suppose that you have both of the partial derivatives and you want to know what function it is, which function it would be that has both of those partial derivatives. Now we know for a function of a single variable, if we have the derivative, we can integrate, and then the integral would be it would be the function that, upon taking the derivative of, you would get what we had initially as the output. So for a function of two variables, we could do the same thing, but that presents another issue, but it's not something that can't be solved for. So let's just say I took, and you can take either one of these, but for the purposes of this video, I'm gonna take the derivative with respect to x. I'm going to integrate partial f with respect to x dx. And I'm going to say that f of x y is equal to that. So obviously the function f of x y is equal to the integral with respect to x of the partial derivative of that function with respect to x. That's pretty obvious, but we have a problem once we integrate it, and I'm gonna have to continue using that same generic nomenclature for the integral of this partial derivative. But once we integrate this guy right here, we end up with a constant of integration. Now this constant of integration, unlike with single variable functions, this constant of integration, on the other hand, is actually a function. It's a single variable function, and the variable that it would be a single variable function of is y. So plus c of y. And the reason for that is, well, just think about it now. If you take the derivative of everything, or the partial derivative of everything with respect to x, then any term that is solely dependent on y will go away. Now, I do want to sidetrack here, actually, for anybody who is not quite familiar with multivariable calculus and partial derivatives. I'm gonna just show a quick example, but let's just say that f of xy is x squared times y. The partial f with respect to x, or the partial derivative of this with respect to x, would be, well, in this case, because I am differentiating with respect to x, y is treated as a constant. So it'd be y times the derivative with respect to x, and when we're working with functions of more than a single variable, we tend to use the partial differential notation. So this right here would be y times the regular derivative with respect to x of x squared. And so that would result in 2xy. And then if we wanted to take the partial derivative of this with respect to y, we would treat x squared as a constant, and then we would take the derivative of the term y. And that would end up resulting in just x squared. Alright, so now that I've crossed that bridge, we have that the function f of xy is equal to whatever you will get once you integrate the partial derivative with respect to x plus some single variable function of y, which is the resulting constant of integration. So now the issue is going to be solving for this function of y. Now let's just say, because we already have the partial of everything with respect to y, we already have partial f with respect to y. That's this term. So let's just suppose now that I differentiated everything with respect to y. So what you do to one side, you must do to the other. So taking the derivative of all this with respect to y, so if I take the derivative of all of this with respect to y, well, this just produces partial f with respect to y. That we already have. And bringing the differential operator in, this would just be this would result in the integral partial squared f partial y partial x dx plus, now the partial with respect to y of c of y, that's just going to be the derivative of c with respect to y. C is only a single variable function anyway, so we don't need to really worry about saying partial c with respect to y. So the result that we come to is quite convenient, really. We have now that partial f with respect to y is equal to the integral of this mixed partial squared f partial y partial x dx plus dc dy. So now if I rearrange this entire expression, I would get that dc dy, or the derivative of c with respect to y, that equals the partial derivative of our initial function with respect to y minus the integral of the mixed partial squared f partial y partial x, the integral of that mixed partial with respect to x. So hopefully at this point your spidey senses are tingling and you can tell where this is going, but this right here is a separable equation, and you would already have what the partial derivative of your initial function is with respect to y, and you would also have the partial with respect to x, so that integral of the mixed partial would be fully solvable. So now the differential of your constant of integration, dc, remember the constant of integration in this case is a single variable function, but the differential of that is going to be all of this right here, partial f with respect to y minus the integral of the mixed partial squared f partial y partial x dx, the integral of that with respect to x times dy. And at this point you can then integrate both sides. So upon integrating both sides, your function, or your constant of integration in this case, c of y, that's equal to the integral of partial f with respect to y minus partial squared f partial y partial x, or the integral of that, dx, dy. So we're not quite done here yet. We earlier proposed a solution that f of xy is equal to the integral of the partial derivative, partial f with respect to x. The integral of the partial derivative of a function with respect to x, and you're integrating that with respect to x as well, plus c of y, this single variable function of y that just so happens to be our constant of integration. And so we've solved for this constant of integration now. So we can finally say that f of xy, actually let me switch colors here. So finally, we can say now that gotta get out my pen. So we can finally say that f as a function of x and y is equal to, let me move everything over here, the integral of partial f with respect to x dx plus this integral right here of partial f with respect to y minus, again, another integral within this, the mixed partial squared f, partial y, partial x, dx dy. And this would be the resulting function f of x, y. So now I encourage you to try to come up with a function, or try to come up with a equivalent derivation now, but start by taking the partial derivative of f with respect to y and integrate that and come up with something that would be equivalent to this.